I think it's working. Okay. So, to rewrite a radical expression, which is what this is, because this symbol here is called a radical. That's a square root. But this one over here is also a radical. That's called a cube root. All right? Just remember that the square root really has a little 2 here that we just don't write because we're lazy. For every other root, you got to put the number that goes there. So the root becomes the denominator of the exponent. So because this is a square root, like if we just had this, that would be the same thing as 5 to the 1/2 power. Okay? But because it's cubed, that's really 5 to the 1/2 cubed. Just looks just like that. And because you are multiplying exponents, when you have a power to a power, when you have this power to this power like that, you multiply those exponents. So 3 times 1/2 is 3/2. So a nice little shortcut is just to remember that whatever the power is goes on top, and whatever the root is goes on the bottom. It's going to be locked, friends. Here, open it with this. I'll give my key back. Okay. That means over here, when I do letter B, it's cubed root of 2, so I know it's going to be 2 to the divided by 3 power. And because it's to the 4th, that just goes up here. Okay. There's also nothing stopping us, thank you, sir, from actually using this power. So let's just stick with B. Like, I can raise 2 to the 4th. 2 to the 4th, which means 2 times 2 times 2 times 2 is just 16. So because 2 to the 4th is 16, this thing here is the same thing as the cube root of 16. So you might also see somewhere along the lines where this is just 16 to the 1/3. But if you put this into a calculator, 16 to the 1/3 is exactly the same as 2 to the 4/3. And that means if you were to slide over here, 5 to the 3/2, because 5 cubed is 5 times 5 times 5 is 125. This is the same thing as 125 to the 1/2. But for our purposes and for your final, these answers that we have right here are how we want to do this. This is totally fine. But if it's multiple choice, I'm just saying, this is also the correct answer for this. Okay. I'm not saying I'm going to try and trick you, but you should know they're the same. Question 2 is just reversing this process. So this is really, it's hard to see the way this is written, but this is really 7 to the 5/2 power. And like we saw in number 1, the denominator really becomes the root. So this is just the square root of 7 like that. And because it's to the 5th power, you can write to the 5th power here. But because roots and powers play super nice, you could also do 7 to the 5th like that in there. Those are both the exact same thing. All right? But I'll write it like this. But again, if the 5's inside on that 7, the square root doesn't really matter. Yeah. So that means here, this is 13 to the 1/4. Let's write that down here. 13 to the 1/4 power really just means the 4th root. Remember, a fraction exponent is really just a root. The denominator is the root we're taking. So it's the 4th root of 13. But the negative that's out front of this thing flips it. So it just moves it down to the denominator. So it is the 4th root of 13, but it's in the denominator of this fraction. Okay, and we can't do the 4th root of 13 in our heads, right? So we would need a calculator for that, but so we would leave it just like that. Same thing with part A was a root 7. I don't know what that is, okay, off the top of my head without using a calculator. But 8 to the -2nd is the same as 8 squared, but it's in the denominator. So it's 1 over 8 squared. And because I can handle 8 squared, that's just 1 over 64. Those are the same number, all 3 of them. All right. So this says, find the value of the expression, 8 to the -2/3, as a fraction in simplest form. So the negative is going to move it down the denominator, so let's do that first. That's the same thing as 1 over 8 to the 2/3. That's what the negative on that 2/3 does. It just puts it right down in the denominator. Okay, and we'll keep using our rules here. That's 1 over, to the 2/3 is the cube root of 8, and then squared. Okay, that's what that denominator does. And the cube root of 8 happens to be 2, so that's fine, but that's 2 squared. and 2 squared is 4. So 8 to the negative 2/3 is just a fancy way of writing 1/4. They're the same exact number. All right, for number 4. For solving these equations, I want you to take note here. Every single one of these equations, A, B, C, and D, just has a single x in it. All right, so there's one x in this equation, there's one x in every equation. And when that happens, your job then is just to get that x all by itself. When there's multiple x's, that's when we got to do a little bit of extra stuff. But when there's only one x, you just want to get it by itself, and we do that by undoing what is happening to x. But we got to do it in the right order. So over here, x is being subtracted by 3, it's being cubed, and then we're subtracting 5 outside of that. So the order in which we undo these, always, if there's a plus or minus attached at the end or the beginning if it's out front, as long as it's not inside of these parentheses here, we want to get rid of that first. So we're going to have 5 to both sides is what that looks like. When you do that, the 5s on the left-hand side cancel, and we get 59 plus 5 is 64. Okay? So now we have this equation here that we're trying to solve. And next thing we got to attack, so we always attack from the outside. All right, so when we're trying to get x by itself, we attack from the outside. That's why we got rid of the minus 5 first. I need to get rid of this cubed. And the thing that undoes a power is a root. So if I want to get rid of a cubed, I need to take the cubed root of both sides, like that. And the cubed root of something cubed is just that thing. The cubed root of 64 happens to be 4. And then we add 3 to both sides here, and we get that x is 7. Again, hope we don't need to write all this, but we're just adding plus 3, like that. And that's our answer. Okay? And if you're taking your final, it makes sense to go ahead and just double check that real quick. And if it's a multiple choice question and the answers are all there, you can plug them in and see which one works, honestly. Okay? But if I put 7 back into this equation, I get 7 minus 3 cubed minus 5. And I'm seeing, does that equal 59? Well, 7 minus 3 is 4 cubed minus 5. 4 cubed is 64 minus 5. And oh my goodness gracious, that happens to be 59. Excellent. All right. Part B, we've got a single x value in here. Okay, it's inside of a square root, so I need to get rid of this minus 4 and this 2 first. I want to get the square root all by itself. Okay, so again, we attack from the outside, and the first thing we get rid of, if it's outside, is plus or minus. So we're going to get rid of that minus 4. So we're going to add 4 to both sides. And what that's going to leave me with is 2 times the square root of 3x plus 1 equals 6. Then we're going to divide by that 2 out front, because we don't want the 2 there. So that is going to be 3. And now we have a root. And just like we did on part A, when you have a power, you get rid of that with a root. So when you have a root, you get rid of that with a power. Now this is a square root, so we get rid of it by squaring both sides. And when we do that, we get that 3x plus 1 is 9. So we're going to subtract 1, which is going to give us 8, and 3x on the left side, right? And then we're going to divide by 3. So we get x is equal to 8/3. And again, just to double check, which is always a good idea when you were taking a major test or just want to know if you're correct, I need to plug this back in and make sure it works. So that will be 2 times the square root of 3 times 8/3 plus 1 minus 4. And my question is, does that equal 2? So we do 2 times the square root, 3 times 8/3. These 3's cancel. That's how multiplying fractions work, right? If you're multiplying them, anything in the numerator can cancel with the denominator. It's really 3 over 1, okay? You could also, if you multiply it straight across, turn that into 24 over 3. But that's just 8, and that's because the 3's cancel here. So we're just left with that 8 plus 1 minus 4. 8 plus 1 is 9. So it looks like that. The square root of 9 is 3. 2 times 3 is 6, minus 4, that is 2. Excellent. Okay, for C. We have another root, but it's a cube root this time. But just like we did with the first two, we're going to do minus 4. Minus 4. Yeah, that leaves me with the cube root over here. Equals 2. Now to get rid of the cube root, we're going to do a power, so we're going to cube both sides. That leaves me with 2x minus 5 is 2 cubed, which is 8. We're going to add 5 to both sides, which is 13. And then we're going to divide by 2, which is 13 halves. All right. And then for d, we just have this single x squared here. So we're going to get rid of the 8 first. I like drawing this little fence here so I know what side's on what, right? I've got a left side and a right side. So we're going to add 8 to both sides. You never want to add 8 on the same side of this dotted line I just drew, okay? It's always got to be on opposite sides of the equal sign. So that's what we're doing. We're doing the same thing to both sides. So the minus 8 and the plus 8 cancel out. That leaves me with 4x squared equals 136 plus 8 happens to be 144. I need to divide by 4 on each side. And that gives me x squared is 36 is what that's going to be. And to get rid of that squared, I need to take the square root. Okay, but when I do that for square roots, not for cube roots, like we did up on number, which one was that? Letter A. When you take the square root, I'm going to put it in blue so you see it. You got to put a plus or minus out front. Okay, because if x squared is 36, x could equal either positive or negative 6. So we'll check that again real quick too. I don't think I checked C. That's all right. If you plug 6 into here, you get 4 times, and we can plug negative 6 in too to check it too like that. That will look like this. And the question is, hey, does that equal 136? Well, negative 6 squared is positive 36 minus 8. And 4 times 36 is 144 minus 8. And 144 minus 8 is 136. Okay. Here we go. So for square roots that involve these negatives, just remember, all you really got to do is break apart like this. Okay, if there's a negative inside of a root, you're going to take that out, and the root -1 is going to become I. That's just the definition of it, and that not root 9 becomes a 3. So it's I times 3, but you usually put the number in front, so we'd write that as 3I. Yeah, the square root of this -48. So remember, when you're breaking down a square root, you always want to use multiplication. We're trying to break this into nice things that I can take the square root of. So 48, we're going to break apart like this, because again, that negative I don't want there. This is just going to become an I at the end, and that's fine. We'll just put an I right there. Root 48, we don't want to use a calculator for that. Like, our goal is to reduce it down and have smaller numbers going in here. So I need to find a number that goes into 48 that has a nice square root. All right, and our numbers that have a nice square root, if you don't remember, are 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16. So these are all the numbers that I want to check. And this goes on forever, right? I can continue squaring these. But the most you'll ever see probably, especially on this final, is I imagine up to 10. The most that we ever really see by hand is like 15 squared is 225. But either way, I need to find a number that's over here. I need one of these, okay? And again, we can keep going, but we don't need to for this question. One of these has to go into this 48. Otherwise, I just can't reduce it, okay? But we can reduce it because 2 of these numbers happen to go into it. 4 goes into 48. So I could rewrite this as the square root of 4, and 4 goes into 48 12 times. This is the same exact thing because 4 times 12 is 48. So they're equal to each other still. So we could do this, and that root 4 really becomes a 2. It's not a root 2, because the square root of 4 is 2. And then root 12 is still here. So you can write root 12 here, and it looks like maybe we're done, but you always got to check, just like when you're reducing fractions, you got to check this square root of 12 to see if another one of these numbers goes into it, and 4 goes into 12 again. So this is I times 2 is still here, and I'm going to rewrite this 12 as root 4 times root 3, because 4 times 3 is 12. And root 4 is really 2. This is a 2 already still here. This I is here, and there's a square root of 3 here. And if I put all of this together, I get 2 times 2. Okay, they're not in a root, so those are 4, times that I. So it's 4I with a square root of 3 left over. And that's the answer to this question. And I'm going to show you how to do that a little bit quicker. Okay, but that's how it goes if you see that 4 goes into there. Now, I'm going to erase this and tell you, if you notice, really, you should always check the bigger numbers just in case. If you notice that 16 goes into 48, then you can still turn this root into an I. Root -1 is I. But now I'm going to write, instead of 4 times 12, which does make 48. 16 goes into 48 3 times. And again, I can always get back to where I came from. So root 16 times root 3 is root 48. But the benefit of how I've written it here is that the square root of 16 is 4. And that's a square root of 3. And as you can see, that's a 4 and an I and a root 3. And that's usually, this and this are the same exact answer. I just like putting them in the order you usually see. And that's with the number out front, the I after the number, and then the square root goes at the very end. Yeah, and the reason the square root goes at the end, it's really just a style thing. But if you had something like root 3, and then you had I and 4, something I used to do when I was a kid is this root would come like a little bit too far, and you're like, well, is the I in the root or not? Or maybe even like that. Okay, the root's only on the 3, so you really want to be careful about how you do it. So I just raised that too much. But it's really just like that. I always put like a little tail on my root so I know what's inside of it and what's not. Okay, so those are all the same thing. Doesn't matter the order because it's multiplication. But generally you put the number out front, the I, and then the root at the end. Okay, so I to the 7th goes like this. You can handle this like this. This is I squared times I squared times I squared times I. That's what this is here. And the reason it's that is because 2 I's, and 1 I. There's really a 1 here. That makes 7 I's. All right, so that's really what's happening. I'll show you another way to do this too if you want. But I squared, the whole point of I squared is that it's a negative 1. So this is really just a negative 1. This is really just a negative 1. This is just a negative 1. And that's an I. And now we can simplify this down. I just does this. I has a pattern, but negative 1 times negative 1 times negative 1 is negative 1. And that's times this I. So this just equals negative I. Okay. Another way you might see your teacher do this is that they might tell you like I to the first power is just I. I to the second power is negative 1. I to the third power is I squared times I, right? There's 3 of them. But I squared is just negative 1 times I, so that's just negative I. And I to the 4th power is really just I squared times I squared. But that's just negative 1 times negative 1, which is 1. And after that, if you do I to the 5th power, that's just I to the 4th power times 1 more I. But I to the 4th power was 1, so this just equals I. So this is like, they call it periodic, or they call it cyclical maybe. If you keep raising I to a power, it just repeats over and over again. So I to the 5th is I. It's the same thing as I to the 1st. If we did I to the 6th, you would just say, well, that's just I to the 4th times I squared. But I to the 4th is just 1, and I squared is negative 1. So this just equals negative 1, which is the same thing as I squared. And if you follow this pattern, you see that I to the 7th is the same thing as I cubed, and that I to the 8th is 1. And you keep going, I to the 9th, I to the 10th. So like I to the 9th is the same thing as I. And that's because, again, that's really I to the 4th times I to the 4th times 1 more I. But each of these I's are just 1s. So it's 1 times 1 times I, which is just I. Okay, so you might see that pattern too. And then when you see that, they might say I to the 7th. What you really need to do, instead of taking away the I squared, you want to take away I to the 4ths. So it's I to the 4th times I cubed. But I to the 4th is just 1 times I cubed. But you still got to do this I squared thing unless you know this pattern that you're doing down here. So this is really just 1 times I cubed. So that's 1 times I squared times I. That's I cubed. 2 I's here, 1 I here. So that's 1 times negative 1 times I. And that's just negative I, which is what we saw in part C. Okay. And then for part D, because we're cubing and there's multiplication in here, cubed and multiplication, powers and multiplication play super duper nice. That just takes the 3 and it cubes it, and it takes the I and it cubes it. So it just does that. You want to simplify that down. So 3 cubed is 27. And I cubed, like I just showed you down here, I'll do it again for you, is I squared times I. This is really this I cubed, and this is really 3 cubed. That's what that 27 is. So it's the same thing as this right here. Okay, but that I squared is really negative 1, so it's really 27 times negative 1 times I. And you would just put the negative 27 out front like that. So this is what your teacher's looking for there. Okay. Operations of complex numbers, you just combine like terms here. So when there's a plus in the middle here, the parentheses don't even really matter. You're going to do 2 plus negative 8. That is negative 6. Then you're going to do 3i minus 2i, and that is positive 1i. When you're subtracting, we'll do the same thing, except if I were you, I would distribute the negative. So this is just going to go into here like that. So we're going to have, now we just combine like terms. So 7 minus 8 is negative 1, and negative 2i minus 6i is negative 8i. All right. And then here, you notice the operation between these two parentheses is a multiplication. So now we got a FOIL, okay? So look, we're going to do 2 times negative 3 and 2 times 7i. So that's negative 6 plus 14i. And then we do negative 3 times negative 3. That's 9i. And negative 3 times 7i is negative 3i times 7i is 21i squared. You are welcome to also do the box here if you like the box better. It's the same idea. Put your two factors like that, like 2 minus 3i and negative 3 plus 7i. This is my negative 6. This is 14i. This is 9i. And this is negative 21i squared. You can see these four things in these boxes are the same thing that I wrote out over here. But the only thing you got to remember is that I squared is really negative 1. So this is really negative 21 times negative 1. And that's really positive 21. Same thing I would do over here too. So this is negative 21 times I squared, which is really, remember this is a negative 1. So negative 21 times negative 1 is really plus 21. Everything else stays the same. You don't need to worry about anything else here except for that I squared term. And now we just combine like terms again. So negative 6i and 21. I'm sorry, negative 6 and 21 make 15. And 14i, that's an I. And 9i make, what is that, 23? 23i. Okay. And just remember, so this squared, it'd be super nice if that just squared here and squared here, but it doesn't. It means multiply it by itself. So this is another situation to do the box or to FOIL, whichever you like better. So I do 5 times 5 is 25. 5 times negative 2i is negative 10i. Negative 2i times 5 is negative 10i. And negative 2i times negative 2i is positive 4i squared. And anytime you multiply these things with these i's floating around there, you're going to get an I squared at the end like this. And that I squared just becomes that negative 1. So instead of plus 4i squared, it's really 4 times negative 1, so it's really a minus 4. But we have minus 10i and minus 10i, 25. And we combine like terms. So 25 minus 4 is 21 minus 20i. Okay. Here we go. This is just so now we're into exponential functions and equations. So we have a car valued at 28 grand starting out, and you can see that from my chart. Look where it's starting at 28. These look like dashes in front of these, but this is just the lines that came off the graph. These are all positives. They shouldn't be negatives. Okay, but it's starting at 28 because it's in thousands of dollars. So it's starting at 28,000, and it is depreciating over time like this. You can see the same thing here. 28. It's decreasing, decreasing, decreasing. All right. And the question is, what is the decay factor? Well, the easiest way to see what the decay factor is not from the graph. It's really hard on the graph to see how fast this thing's decaying. I mean, you see a picture of it, that's really nice. But to tell exactly what it is, that's kind of hard. So the easiest thing to do is to see, well, by what percent did these change? And when I say that, what I'm really saying is how much is left over from what was there originally. So just take any number. I'm taking this number first and divide it by the number before it. All right, and if I had my calculator ready, you would see that this equals something. There it is. Come on, Smart View. It's happening. There it is. Okay, so if we take 22.96 and divide it by 28, how'd you guys do? Did you own everybody? You get 0.82. So 22.96 divided by 28 is 0.82. And I promise you, if this is a real exponential equation, if you take any of these numbers on this chart, oh my God, come on. any of these numbers on this chart and divide it by the one before it. Look, let's just take this 12.659409. So 12.659409, and we divide it by the number directly before it, which is 15.438304. Watch what happens. Look at this magic. Oh my gosh, 0.82. Oh, good morning. So we get 0.82. It's 0.81999999, but it's really just 0.82. That's just rounding error. Okay? So the decay factor here, how much we are moving down by. So we're really, let me see here, this is a little complicated. 0.82 is really 82%. Okay? So that means the car is keeping 82% of its value. That's really what's going on there. But the decay factor is how much are we losing. So if I'm keeping 82%, think about that. If you took a test and you got an 82% out of 100, that means you must have gotten 18% of the points wrong. So we lost 18%, and the decay factor of this is really 100 minus that 82, well, 1.0 minus 0.82, which is 0.18. Actually, I think I'm lying to you. I think it's just the 82. There we go. Sorry. We're losing 18%, but we're keeping 82%. So we'll say the decay factor is 0.82. Okay. Let's finish number 2 here. If we put this much money into an account and it's accruing interest at this rate, depending on how often it's compounded, we can determine how much money is going to be there. So it looks like this. If it's compounded annually, that means once a year. That means we're taking my 4,200. We're gaining 5.4%, which means we're multiplying it by 1.054. Remember, you move this decimal 2 times, which would be 0.054, and you're adding 1 to that. Your teacher might say divide it like this: 1 plus that percent. Okay, and if we're gonna let it sit for 10 years, then it just becomes that. So if we do that in a calculator, we get 4,200 times 1.054 to the 10th power. And that means we're going to have a whopping $7,106. Does it say the nearest dollar? No. So we'll say 7,106 point something, 49.
Smith.
Good morning.
Good morning. Can I go to the bathroom?
Go ahead. Okay.
Are we doing anything to
If we're compounding it monthly, hold on, let me pause this video here.
Yeah.
Okay. If it's compounded throughout the year, then we got to use our formula, which was the amount of money we have in our account is equal to the principal invested, that's P, so that's 4,200 in this case, 1 plus the rate as a decimal over the number of times it's compounded, and this seems kind of complicated, but we're just going to plug into this thing. So for B and C, this is the same formula we're going to use here. So for B, the amount of money in that account is the 4,200 that we've invested times 1 plus the rate is 0.054, and if it's compounded monthly, that's 12 times a year. And we raise that to the 12. This number on the bottom is always the same as this number here. Okay, so if there's a 12 down here, there's a 12 right here. And it's for 10 years, so we put a 10 up here. And we're just going to drop that into a calculator and make it do all the heavy lifting for us. So we're going to do 4,200 times 1 plus 0.054 divided by 12, close that parenthesis, raised to the 12 times 10. 12 times 10. That's going to tell me 7198.50. Okay, so you see it's very similar to when it's compounded annually, but we get $92 more essentially if it's compounded monthly. If it's compounded daily, I'm going to use the same exact formula, except those 12s are going to become, if it's compounded daily, 365. So let's do that down here. The amount of money we have is the 4,200 invested times 1 plus 0.054 over 365 to the 365 times 10. And that's going to be 4,200, 1 plus 0.054 divided by 365. That's raised to the 365 times 10 years. And you'll see this a little bit more than we got when we compounded it monthly. 7206.94. Okay, so just a little more than we got when compounded monthly. And if we compound it continuously, this is the only one that has a different formula. That's when we got the e to the RT. So for this, it's the amount of money is the principal invested times e to the RT. So that's my 4,200 times e. The rate is still 0.054, and the time is 10. So that's 4,200. To get to e, it's second, this ln button here next to the 4. That's e to a power, and we're going to put in 0.054 times 10. And hit enter, and we get 7207.23. Okay. You can see over 10 years, it's not that much of a difference from daily. But if you invest in more money, you can see that it's definitely going to be more. And if you give it more time, it'll also be more. All right. So here we have a school has this population. It's growing 5% every year. How many students will there be after 30 months? Well, the only trouble with this is every year, and this is in months. So 30 months is 24 months plus 6 months. That says months. Oh my gosh. 24 months is just 2 years. And 6 months is 0.5 years. So we just got to get this in terms of years, since our rate is in years. So this is 2.5 years. Cool. You also could have done 30 divided by 12 months. Okay. And that will also give you 2.5 years. That's the same math. All right. But this is similar to what we did before in part A of number 2. So the number of students, which I'm just going to call amount of students, is the number we started with, which is 1350, times 1 plus the rate of growth, which is 0.05, raised to the number of years, which is 2.5 in this case. So if we use our calculator for that, it's 1350 times 1 point, I forget already, was it 2.5%? No, 5%. 0.05 to, oh, it was 2.5 years. The 2.5. And we're going to have 1,525 students to the nearest student. So we'll say 1,525. Okay. Here we have the doubling. We have 3,200 ants, and they're doubling every 6 weeks. How many ants are there after 20 weeks to the nearest whole number? So to double, you multiply it by 2. So we're going to say that the number of ants is equal to the amount we started with times 2, because it's doubling, but it's doubling every 6 weeks, so it's to the 20, because we don't know how many are there after 20 weeks, but we got to divide that by 6, because it's every 6 weeks. And the equation for that really is the amount you started with, which I'm going to call P again, times 2 to the T over, if it's every 6 weeks, you put it over 6. So this is another one we just drop into a calculator, which is 3,200 times 2 raised to the 20 divided by 6, which is 32. It's a lot. 32,253. That seems too big. It's going to double 6,400. It's going to double 12. It's going to double again. Yeah, okay. 30. It's more than I expected, but it's 32,254. That's going to be ants. Okay. And what I was just doing in my head there, I thought that was too big. Okay, so what I just did was, I said it's going to double every 6 weeks. Okay, so I just made sure this made sense in my head. So if I start with 32, after 6 weeks, doubling that is 6,400. Okay, after 12 weeks, which is 6 more weeks, it's going to double again, so that should be 12,800. And after 6 more weeks, which is 18 weeks, it should double again, so that's going to be 25,600. That's just double and double. So I knew it had to be bigger than this number here, 25,600, and it was 32,000. All right. And here we have something which half-life So this is the same thing as the last one, except instead of multiplying by 2, we're going to multiply by a half. So we have 75 grams to start. So the amount left over is 75. We're cutting it in half every 8 years. Okay? So it's raised to the amount of years divided by 8. That's it. That's how all those numbers play. Okay. Rewriting these as a log. This is 3 is equal. So the base here is 5. So the 3 comes down, and you put a log on the other side with base 5 of that 125. Okay? Same thing happens over here. The negative 3 is going to come down, and it's going to be log base 5 again of 1 over 125. Okay? Here the base is 64. So the negative 1/3 just comes right down, and on the other side we have log base 64 of a fourth. Okay. And then 2 is just writing an exponential form. It's just undoing this. So the base is 8. So the log goes away. We just have 2 equals 8. This becomes the exponent. So it's this to this power, like that. Okay, you see it here too, like 5 to the 3rd is 125. That's what this says right here. All right. This says solve. We got a couple different flavors of these things here. But if you see x up in an exponent, you're going to have to use a logarithm or get the same base. Those are the only 2 ways we're going to do this. So we got to get rid of this 8 first. And when we divide by 8 on both sides, 128 divided by 8 is 8 times 2. Is it 16? I think it's 16. Okay, it is 16, definitely. Okay, so we could use a logarithm here and just rewrite it as a log, which is log base 2 of 16. That's fine. But I also know that 16 is just 2 to the 4th power. So this also just equals 4. Okay, like log base 2 of 16 is 4. That's what that equals. Over here, 81 is the same as 3 to the 4th power. So if 3 to the 5x plus 1 equals 3 to the 4th, then 5x plus 1 had better equal 4. And you solve that, you go subtract 1 and divide by 5. You're going to get 3/5. Okay, up here, we're going to divide by 6 first. That's going to give me this 3. What's up, Mr. Laser? I've got to rewrite this exponentially, which is going to make this. I got to make a video for my Algebra 2 kids. And we can turn that into a decimal on our calculator, which is 1.0986. Then we got to subtract 1 and divide by 3. I'm just going to do it on my calculator as well. So we'll do -1, boom, divide by 3, boom, 0.0329. Whoa, I didn't want to do that. 0.0329. Okay. If you want to solve this one, we got this exponential over here, okay, so we see that x is up in the exponent. Going to have to use a log, but we got to get the exponential thing by itself first. So we're going to do -7 on each side, and we're going to divide by 2 in a second as well, okay? So it's 2 to the 4th power, 2 times 4, to the power of 2x minus 3 equals 14, and then we're going to divide that by 2, and that's going to give me 7 here, like that. Now, because 4, unlike the last, well, A and B, I guess, we can't get 4 to a power to equal 7, because 4 to the first is 4, 4 to the second is 8. I don't know what 4 to a power is going to give me 7. 4 to the second is not 8. 4 to the second is 16. There we go. Okay, so I can use logs to do this. So we can do ln if you want, but I think it's easier to just rewrite this as a logarithm by bringing the exponent down, and on this side, again, because the base was 4 here, the base of my logarithm is also 4, like that. All right, and I want to know what that is as a decimal just so I can get this answer. So I'm going to grab my calculator. We can do this 2 different ways. If you hit, so on a lot of calculators these days, if you hit math, that's right here, and then you hit up twice, you see this log base option. Hit enter on that. I want log base 4 of 7. And that's going to spit out this decimal, 1.404 is what I'm going to say. If your calculator doesn't have the option to do the base, you also could do ln of 7, because it was log 7 here. But the base, we divide by the base. And that's going to spit out the same number if you do that. And I'll show you on the calculator real quick. You can just hit ln of 7. This is also nice because you don't have to go into the math menu. Divide it by ln of 4. And that's going to spit out the same exact number as you can see. And now I just got to solve this out. So I'm going to add 3 to both sides. So it's going to give me that 2x is, 3 added to this is 4.404. And then to solve for x, we need to divide by 2. And that's going to make this 2.202. Okay. Here we have a log, and x is the base of the log, actually. So anytime you have a log and there's a variable associated inside of there, we got to rewrite it exponentially. But remember, this is the base, so this to this power, so x to the 1/2 equals what was over there, 8. That's how that goes. It's just rewriting it. And since it's to the 1/2 power, to get rid of that, remember, 1/2 power just means square root x. They're the same thing. So to get rid of those, I'm going to square both sides. So that means x is just 64. And for f, same thing. We have a log with x is in the inside now instead of being the base like it was back there in e. Okay, but I'm still going to rewrite that exponentially. And if you don't see a number down here, remember, there's really a 10. So every other log has to have a number down here. It has to have a base. But if it just says log and there's no number, it's base 10. So this becomes x equals 10 to the second power. And x equals 10 to the second is the same thing as 100. So that's our answer for that guy. All right. The transformations of functions, which we are still kind of doing in class for me. But just to name the transformations that are applied here. Okay, so the parent function first is just x cubed. Okay, and we would call that a cubic if we had to name it. Okay, and the transformations that happen are the -3 does two things. It reflects over the y-axis. That's because it's negative. Sorry, over the x-axis because it's negative. It vertical stretches by a factor of 3. And then it translates it left and down. So it's left 2, I'll put this in 1. Left 2, down 8. That's what that does. Okay. And if we had to graph it, which it doesn't say to, but we can, the cubed root of x looks like this. So if we were to graph that with these transformations, it would be left 2, it would be down 8. Right here, boom. It's flipped over, so it's going to have this basic shape now, okay? But it's stretched. So it's going to be a little bit steeper, but it's still going to go like this. So that's what that graph looks like. Over here, the parent function is square root of x, which we can name as square root. Okay, and this is going to have a vertical compression, or you can just call it a shrink if you want, by 1/4. And the negative on the inside, so it's not the same as putting a negative out here, it's on the inside, that's going to reflect left and right over the y-axis. So root x looks like this. So if we reflect that over the y-axis, it's going to go this way. But the 1/4 kind of crushes it some, so it's going to come out smaller like this. Okay. This is an absolute value graph, so the parent function is absolute value of x. So I'll write that, and I'll just write absolute value. And it's only a translation, so it's going to go 4 to the right and up 7. So 4 right, up 7. 7 up. Okay. And w of x over here, this is an exponential. So the parent function, oh, let's graph this over here too, I forgot, sorry. So absolute value of x looks like this. We're going to move it 4 to the right. So it's 1, 2, 3, 4, and up 7. 1, 2, 3, 4, 5, 6, 7. It's going to be way up there. That's where the corner is going to be, the point, and it looks like that. And here we have an exponential function. The parent function is 2 to the x. And we'll call that exponential. Okay, and the negative out front is going to reflect over the x-axis. So reflect over the x-axis. It's going to move it 1 right and 2 up. That's because the minus 1 does 1 to the right, plus 2 does 2 up. Okay. Even, odd, or neither. Remember, even just means that it looks the same on both sides. So an even graph looks like this. It's just whatever it does on one side, it does on the other. That's even. Okay. So you can see that C is the same on the left and the right, split by this axis here. So this is an even function. All right. Odd means it's the same but flipped over. So odd, like if this side goes up like this side does the same, but it goes down. And you can see that this is an odd one. What's up, Russell? Why are you still here?
This one just happened.
What happened?
They moved the Orioles game.
Yeah, I saw.
4:30.
I know, man, so I'm going to be late to it now.
Oh. No, I didn't go in the physics field.
Okay. Oh, I paused it, and I don't remember what I was saying. I think I was talking about odd functions, and we said that this guy over here is odd because this side does the exact same thing as this side, but upside down. So that's what an odd function is. Okay? And then B, I don't know why it says odd down here. Come on now. B is going to be neither, because although it does have symmetry, it does look the same if you fold it over this line. Even and odd specifically refer to symmetry over 0. So even refers to symmetry over this line right here. And you can see this graph does not look the same on both sides of that line. And odd speaks to symmetry over the origin, which is this point right here. You got to be able to rotate it 180 degrees and get the same thing. So this one is neither, because it's not the same on both sides of the y-axis, or upside down on both sides of the y-axis. Okay. If you're given a function like this and you have to tell if it's even or odd, again, the rule's the same. If you look on the right side of the y-axis or the left side of the y-axis, they should be the same thing. And what that really equates to is if you plug values in on opposite sides of the y-axis, let's think about this here. Here's x equals 1, here's x equals negative 1, right? When I plug 1 into here, I get 1 squared plus 4, which is 1 plus 4, which is 5. So at 1, this thing is at 5. We'll say that's 5 right here. If I plug negative 1 in, negative 1 squared is still 1, plus 4 is still 5. So this thing at negative 1 and 1 is the same on both sides. Now to be even, that has to be true for all points. But if you're just trying to show if this is even or odd, one way to do it is to pick a few points so we could do 2 and negative 2. Okay? So if we plugged in 2 into this thing, we would get 2 squared plus 4, and that equals 4 plus 4, and that's 8. So by the time we get to 2, I'm up here at 8. All right, we'll say that's 8 right here. And if I plug in negative 2 and square it, I'm going to get positive 4 plus 4. It's still 8. So you can see on both sides of the y-axis, this is the same for those 2 points. And the way you show it for all points, which is a little bit more confusing because you don't plug a number in, you plug in negative x, is, like I said, so you got to take this function and you got to plug in negative x where that x is. So it looks like this. And as long as that equals the same thing we started with, which is x squared plus 4, then we're going to know that it's even. If it equals the opposite of what I started with, then it's odd. But negative x squared is just x squared. So if I plug negative x in, I get the same thing I started with. And that means this is even. All right, and then finally, the last way you can tell that this is even is you can know what this graph looks like. Like we're supposed to, at this point, know what x squared looks like. X squared looks like this. Okay, that's x squared. If I add 4 to that, it just shifts it up 4. So that graph looks like this. But we're going to be able to tell that that's the same on both sides of the x and the y, or the y-axis, I mean. So since it's the same on both sides, that is an even graph. Okay. And over here, same thing. I'm just going to plug in negative 1 and 1 because most functions aren't even or odd. So if I plug in negative 1 or positive 1 into this, we'll do first. Okay, if I plug in positive 1, it looks like that. 1 cubed is 1 plus 1 plus 1. 2 times 1 is 2 plus 1, and that equals 4. So if this is even, then when I plug in negative 1 to where those x's are, I've got to get the same value. If it's odd, I got to get the opposite of it. So this down here has to either equal 4 if it's even, or negative 4 if it's going to be odd. If it doesn't equal one of those numbers, then it's not even or odd. So negative 1 cubed is negative 1 plus negative 1 like this, plus 1. Well, 2 times negative 1 is negative 2 minus 1 plus 1, but that equals negative 2. Since it doesn't equal negative 4 or 4, this graph is neither even or odd. Okay. Yeah, that's good. I'm trying to think if we could explain this one other way here real quick, just to make this easy for you, because I like having you guys do this a couple different ways. That way you can check your work. Okay, so let me erase all this junk for a second. Actually, I don't want to erase all that junk. Okay. This was neither. Sorry, let me redo this. Another way you can tell real quick is just by looking at the exponents on the x's. If it's just an algebraic thing, x to powers, if the power on all the x's is even, then it's going to be an even function. And I know this 4 over here doesn't look like it has an x, but it actually has an x to the 0 on it. And 2 and 0 are both even numbers. And that's why this ends up being an even function. I'll show you. Over here, I'm just making a little video. This one really has x to 0 on it. These exponents, there's really x, this is to the first. These exponents are odd, while this exponent is even. And if you have an odd exponent and an even exponent, then the function is going to be neither even nor odd, which is what happened. Okay. So then down here, let's finish this up real quick. I want to take x squared and translate it 4 to the right. That puts...
I think we're going to be the only 3 people here.
That's okay. So minus 4 like that moves it 4 to the right, and down 2 units is a minus 2 like that. Okay, so over here, if I want to reflect it over the y-axis, that means I need to make x negative. So reflect over the y-axis means make x negative like that. Okay, and translate up 4 units means add 4 at the end. So this becomes ln of negative x add 4. Okay. A vertical stretch means multiply by 2. So this is going to become 2 cube root like that. And it should just be x in there, but I also want to move 4 to the left. So that means we add 4 on the inside. And then finally, I want to take 2 to the x. I want to compress it by a factor of a half. Well, that just means multiply it by a half like that. Reflect it over the y-axis. I didn't do any over the x-axis. Okay, that's fine. Reflect it over the y-axis, which is going to make my x negative. Wherever the x is, just becomes negative. And then we're going to translate it down 3 units. So at the very end, you put a minus 3. And that's it.